Last time we were talking about the properties of gases and how their molecular interaction determines those properties, and we ended up with things that I hope make a lot of sense, like if gases are compressible because if they have a lot of space between them, and if you squeeze them then you can get them closer together. What we want to do now is we want to take some of those common sense things, let's say, and turn those into mathematical relationships, and that's what we call the gas laws. Now the basic idea of what we're going to do over the next little bit today and next time is we're going to look at three basic gas laws, and the names of them are, sorry, before I give you the names, they're mathematical formulas, and that's what we mean by gas laws. And those are the three that we're going to look at. Now you don't need to know the names because we're never going to attach the name to the formula. We just want to be able to use them. And then what we're going to do is we're going to see what happens when we combine them all, and we get something called the combined gas law. Starting off with Boyle's law, and again, you don't need to know who Robert Boyle was or when he was active, when he was alive. You don't need to know that his father was British nobility. He was the Earl of Cork, which sounds kind of weird until you remember that Cork is an area, like a province in Ireland. Not that it matters. He looked at the relationship between pressure and volume of a gas when the temperature was being held constant, and he found out that there's an inverse relationship. And what that means is if you increase the pressure, you're going to decrease the volume. You're going to squeeze the volume down. Whereas if you decrease the pressure, let the pressure off, then the volume can get larger and it'll expand. And he turned that into a mathematical formula, which we see here, V1P1 equals V2P2, where the ones and the twos represent the set of conditions. So the first set of conditions, V1P1, and the second set of conditions, V2P2. And what's useful to do, and we'll walk through an example, and I encourage you to pay particular attention to what's going on, but also strongly encourage you to push the buttons to actually do the calculations here. The question is going to look something like this, where you'll be told that a gas occupies a volume, here I've got 750 milliliters at a certain pressure, 360 kilopascals. And then you're asked for a new volume when the pressure changes to something else, like 150 kilopascals. At no point will you be told the temperature is held constant. You just won't be told anything about temperature. So to kind of look ahead at our formula and the information that we have from the question, I'm given a volume and two pressures, and it's important to line them up with each other properly. So you don't have to identify them in a column like this. I sometimes write in the question or above the question or above each number, whether that's a V1 or a P1, because I find a lot of people get them mixed up and they end up calculating the wrong thing because they've, well, flipped the pressures around. So if my Boyle's law is V1P1 equals V2P2, I need to find the second volume. Now I like to rearrange the formula first, but you could put the numbers in first and we'd end up doing the same thing. So to find the second volume, I'm going to be putting the numbers in like so. You don't have to put the units in with the numbers in the calculation. I like to, but I also think it's easier for you to figure out what's what when I include the units. You would absolutely need to have units in your final answer here of 1800 milliliters. Now I know it's 1800 milliliters because my first volume was also in milliliters. If my first volume was in liters, then my second volume would also be in liters. That's pretty much all there is to Boyle's law, which takes us to Charles' law. And again, you don't need to know that it was named for Jacques Charles. You don't need to know his dates of birth or anything else like that. You do kind of want to understand that his investigation was the direct relationship between volume and temperature at constant pressure. Now, again, the constant pressure part isn't so important because you just won't be told anything about pressure. The direct part is important, and what that means is if I increase the temperature, I'm going to increase the volume, and that's probably something we've known for a long time. You heat something up and it expands. Hot air expands. Mathematically, though, he turned that into a formula of looking like this. So volume 1 divided by temperature 1, volume 2 divided by temperature 2. Now you can sometimes express this flipped around where both sides are flipped. However, for our purposes, almost every single time we're going to be using this to find a volume. I probably shouldn't say almost every single time, but I hate saying every single time, I hate making those promises. But we're almost always going to be finding a new volume, so the very first formula on the left makes more sense. Volumes on top. The other thing that is extremely important with this, and I would put a star beside this, is temperatures have to be in Kelvin. I cannot use Celsius temperatures. Here's the thing though, I will tell you a Celsius temperature because that's how we measure temperature, but then you're going to have to convert it to Kelvin. So as an example, again, you'll be given information about the volume and the temperature of a gas and be asked to find the new volume at a new temperature, possibly a new temperature at a given volume, but probably not. So then we'll use the formula that we have and the information that we have. And again, I like to write down the stuff that I know, particularly for this one, because I have to do something additional with my temperatures other than just identify them as 1 and 2. So I have to add 273 to each temperature. Okay, now I go back to my formula. I'm looking for volume, I'm looking for the second volume. So what I do is I like to rearrange first, but I'll show you an example in a couple of minutes where we put the numbers in first in case that's where you're comfortable. And then I put my values in. Again, you don't have to have units in the calculation. I like to, but it helps you find them back a little bit more quickly. And then the new volume is going to be 511.7 milliliters. Again, first volume was milliliters, so the second volume is going to be milliliters. Guy-Lussac, again, named after somebody who, actually, I shouldn't say named after somebody, he named it after himself. And he looked at the direct relationship between pressure and temperature when the volume was constant. So basically we have our pressure, temperature, and volume, and we're looking at each one of these things in pairs. That's all there is to it. If I increase the temperature, I'm going to increase the pressure. Okay. Now, Charles' law said if I increase the temperature, I'm going to make that volume get larger, but if I can't make the volume get larger, then the pressure will go up. Okay. Very much like Charles' law, I've got this relationship where pressure's on top, temperature's on the bottom, pressure this time instead of volume. And again, like the other one, if I'm looking for temperature, it's more convenient to have the temperatures on top, but I'm pretty much always going to be looking for a new pressure in this course. And like before, the temperature must be in Kelvin all the time, and I would put a star beside that as well. To look at an example, you'll sometimes be given hints and clues about these things, but there's no reason why I wouldn't just tell you the information. Again, you're not told anything about volume, so obviously the volume doesn't matter, it's not changing, and I'm going to look at the information that I have and what I know and change my temperatures to Kelvin, and then I'm going to put those in. Now, some people like to put the numbers in first, so it's an example of that. So it would end up looking like this, where I'm solving for the second pressure, which means I'm going to multiply both sides by 263 to get it out of that side and get pressure all by itself. And I end up with a second pressure of 339.4 kilopascals. My first pressure was in kilopascals, so my second pressure is in kilopascals. That's all there is to it. So I've listed off the three formulas that we are most likely going to be using and the reminder about the temperatures. You will always have access to those temperatures, sorry, not to the temperatures, to those formulas and the temperature conversion, but if you don't think to use it or if you don't look to find the formula, then of course that's going to be a bit of a problem. We'll talk to you another time.